In this video, we're going to look at the limitations of perceptrons. These limitations stem from the kinds of features you use. If you use the right features, you can do almost anything. If you use the wrong features, they're extremely limited in what the learning part of a perceptron can do. And that's what caused perceptrons to go out of favour. And it emphasises that the difficult bit of learning is to learn the right features. There is still a lot you can do with learning, even if you don't learn features. For example, if you want to say whether a sentence is a plausible English sentence, you could hand define a huge number of features and then learn how to weight them in order to decide whether a particular sentence is likely a good English sentence. But in the long run, you need to learn features. So the reason that neural network research came to a halt in the late 1960s and early 1970s is that perceptrons were shown to be very limited, and we're now going to understand what those limitations are. If you're allowed to choose the features by hand, and if you use enough features, you can make a perceptron do almost anything. Suppose, for example, we have binary input vectors, and we create a separate feature unit that gets activated by exactly one of those binary input vectors. We'll need exponentially many feature units, but now we can make any possible discrimination on binary input vectors. So for binary input vectors, there's no limitation if you're willing to make enough feature units. But of course, that's not a very good strategy for solving a practical problem, because you need an awful lot of feature units, and it won't generalize. You can't look at a subset of all possible cases and have any hope of getting the remaining cases right, because those remaining cases require new feature units, and you don't know what weights to put on those feature units. Once you've decided the hand-coded features, that is, once they've been determined, there are very strong limitations on what a perceptron can learn to do. So here's a classic example. What we're interested in is, what can you learn to do with the binary threshold decision unit, that is, by changing its weights? And we're going to show that there's very simple things that it can't learn to do. So the simplest example is, consider a problem in which there's two positive cases and two negative cases. And the features are just single-bit features that have values either 1 or 0. So the two positive cases consist of both features being on, in which case the right answer is 1, or both features being off, in which case the right answer is 1. And the two negative cases are when one feature is on and the other one's off, in which case the right answer is 0. So all we're asking the binary threshold unit to do is decide whether the two features have the same value. And it can't even learn to do that. We can prove that algebraically. Those four input-output pairs that I showed you give rise to four inequalities, and it's impossible to satisfy them. So the first positive case, when the two feature values are 1, the output should be 1, that gives us the inequality that 1 times W1 plus 1 times W2 has got to be greater than the threshold, so we give an output of 1. And the second positive case gives us the inequality that 0 times W1 plus 0 times W2 must also be greater than the threshold. And the negative cases give us the inequalities that 1 times W1 plus 0 times W2 must be less than the threshold, and similarly 0 times W1 plus 1 times W2 must be less than the threshold. Now if you take those first two inequalities and you add them up, you get that W1 plus W2 must be greater than twice the threshold. And if you take the second two inequalities and you add them up, you get W1 plus W2 must be less than twice the threshold. So there's clearly no way to satisfy all four inequalities. Or to put it another way, if you look at the binary decision unit, where we're going to put the threshold as a negative weight on an input line that always has value of 1, if you take that binary threshold unit shown at the bottom right, there's no way to set the threshold and the two weights so it gets all 4 cases right. We can also see this geometrically. So we're going to imagine a data space now in which the axes correspond to components of an input vector. So in this space, each point corresponds to a data point, and a weight vector is going to define a plane in this space. So it's just the opposite of what we're doing with weight space. In weight space, we made each point be a weight vector, and we used a plane to define an input case. Of course, that plane was defined by an input vector. Now what we're going to do is we're going to make each point be an input vector, and we're going to use a weight vector to define a plane in the data space. The plane defined by the weight vector is going to be perpendicular to the weight vector, and it's going to miss the origin by a distance equal to the threshold. So here's a picture. You see the 4 data cases there, and for the 2 data cases in red, we need to give an output of 0, and with the 2 data cases in green, we need to give an output of 1. That means we need the green cases to be on the side of the weight plane where the output is 1, and we need the red cases to be on the side where the output is 0, and we obviously cannot arrange the weight plane so that that's true. We call a set of cases like that where there's no hyperplane that will separate the cases where we want the answer to be 1 from the cases where we want the answer to be 0. We call that a set of training cases that's not linearly separable. An even more devastating example for perceptrons, because it's much more general, is when we try and discriminate simple patterns that have to retain their identity when you translate them with wraparound. I'll give you an example of what that means in a minute. But the idea is that we want to recognize a pattern, and we want to recognize it even when it's translated. So suppose we just use pixels as the features. The question is, can a binary threshold unit discriminate between 2 different patterns and call one positive example and the others negative examples if they've got the same number of pixels in them? And the answer is no, it can't discriminate 2 patterns that have the same number of pixels if that discrimination has to work when the patterns are translated and if the patterns can wrap around when they translate. So if you look at these examples of pattern A in a one-dimensional image, pattern A has 4 pixels that are on, those 4 black pixels. It's like a little barcode. And it's the same pattern when we translate it a bit to the right. And we're going to allow ourselves to translate the pattern so it goes off the right-hand end and comes back on the left-hand end. So the third example is the same pattern that's been translated with some wraparound. And pattern B, it also has 4 patterns, but 4 pixels, but in a different arrangement. And in the third example of pattern B, it's been translated with wraparound, so that's still an example of pattern B. And for 2 sets of patterns like that, a binary threshold unit cannot learn to discriminate them. And here's the proof. What we're going to do is we're going to consider that for the positive examples, we have pattern A in all possible translations. Now, since pattern A has 4 on pixels, that means if we look at any pixel on the retina, there'll be 4 different positions in which we can put pattern A that will activate that pixel. So each pixel will be activated by 4 different translations of pattern A. That means that the total input received by the decision unit over all those various translations of pattern A will be 4 times the sum of all the weights in the perceptron, because each pixel will activate the decision unit 4 different times. And so summed over all those patterns, we'll get 4 times the sum of the weights. Now consider pattern B. We're going to make the negative cases be pattern B in all possible translations. And again, each pixel will be activated by 4 different translations of pattern B. So the total input that the decision unit receives over all those different translations of pattern B will again be 4 times the sum of all the weights. But the perceptron, in order to discriminate correctly, has to have weights so that every single case of pattern A provides more input to the decision unit than every single case of pattern B. And that's clearly impossible if, when you sum over all these cases, all those different versions of pattern A and all those different versions of pattern B provide exactly the same amount of input to the decision unit. So we've proved that a perceptron cannot recognize patterns under translation if we allow wraparound. That's a particular case of Minsky and Pappert's group invariance theorem. And that result is devastating for perceptrons. It was historically devastating. Because the whole point of pattern recognition is to recognize patterns that undergo transformations and see that they're still the same pattern despite the transformation. Like, for example, translation. And when Minsky and Papert showed that a perceptron couldn't do that if the transformations formed a group, that is, the learning part of a perceptron couldn't learn to do that, it became clear that the claims that had been made for what perceptrons could learn were somewhat exaggerated, and that to get them to do anything interesting, you had to choose just the right features to make it fairly easy for the last stage to learn the classification. So the translations with wraparound form a group, and Minsky and Papert proved a general theorem that transformations that form a group make it impossible for a perceptron, for the learning part of a perceptron, to do the recognition. The perceptron architecture can still do the recognition, but you have to organize the features so they do the difficult part. So we have to have multiple feature units that recognize informative subpatterns that tell you something about what class it is, and we have to have separate feature units for each position of those informative subpatterns if we're trying to recognize under translation. So the tricky part of pattern recognition has to be solved by the hand-coded feature detectors, not the learning procedure. The temporary conclusion from this is that perceptrons are no good and therefore neural networks are no good. The longer-term conclusion is that neural networks are only going to be really powerful if we can learn the feature detectors. It's not enough just to learn weights on feature detectors, we have to learn the feature detectors themselves. And the second generation of neural networks, which we'll come to in the next lecture, was all about how you learn the feature detectors. But it took 20 years before people figured out how to do that. So networks without hidden units are very limited in what they can learn to model. If we have more layers of linear units, it doesn't help because everything's linear. We can make them much more powerful by putting in hand-coded hidden units, but they're not really hidden units because we hand-coded them. We told them what to do. It's not enough just to have fixed output nonlinearities. What we need is multiple layers of adaptive, nonlinear hidden units. And the problem is, how can we train such nets? We need a way to adapt all the weights, not just the last layer like in a perceptron. And that's hard. In particular, learning the weights going into the hidden units, that's equivalent to learning features. And that's a hard thing to do because nobody's telling us directly what the hidden units should be doing, when they should be active and when they should not be active. And the real problem is, how do we figure out how to learn those weights going into hidden units so that the hidden units turn into the kinds of feature detectors we need for solving a problem when nobody is telling us what the feature detectors should be?